Hello, everyone. So today we are going to introduce the ideas of valence bond theory. This is going to be our building block to help understand the electronic structures of molecules. So it is worth noting that we are going to be making a lot of approximations for valence bond theory, but it's a good starting place to see how our atomic wave functions can translate into more molecular scale functions. So the major idea behind valence bond theory is just like we used, why, just like how we can build molecules by putting together atoms. One of the simplest ways we can build up an entire molecular wave function is if I do the same thing with my atomic orbitals. So instead of just adding one atom plus one atom, I can build one wave function plus another and then worry about normalization and all of the other things that come along with it. So, because when we build up our chemical bonds, they come from the overlap of our valence atomic orbitals. So when I put two atomic orbitals together, the overlap in between those two orbitals gives me a bond. Consequently, we call this method valence bond theory. And we can treat this for a very simple system, the hydrogen molecule ion, or cation. And again, we can treat this as the idea of I have a single electron, which will be spread over my two wave functions, and the bond will come from the overlap between the two wave functions. So I can build this up from the fairly simple idea. If I have one wave function, I can simply add my two atomic wave functions together, generates my new molecular wave function, and then again, don't forget that normalization constant. So this gives me the simplest form of an atomic wave function, and we'll deal with this guy a little bit later. What we're going to try and focus on now is what happens when I put two electrons in here and I make it a true molecule. So again, I start with one electron spread over two atoms. Well, the simplest way I can try and build up a multi-electron atom is a molecule is going to be very similar to the way I built up a multiple electron atom, where I start by putting one electron on A, one electron on B, add them together, deal with the normalization constant, fairly straightforward. But we run into the same exact problem that we did when we were dealing with the multi-electron atom, and that's electron indistinguishability. Because how do I know that electron 1 is around A and not around B? And how do I know that electron 2 is around B and not A? Because in truth, they're going to be around both. So I have two possibilities, electron 1 on A and electron 1 on B. So in order to deal with indistinguishability and still ignoring spin, I have to go ahead and look at the combinations of having each electron on each orbital. We can then possibly combine these in a symmetric or in an asymmetric fashion, with again the symmetric function being portrayed by having by adding the two functions together, and the asymmetric referencing when I take the difference of the two wave functions. So let's look at this a little bit more visually. So the simple case is going to be the symmetric combination. And because when I'm dealing with a 1s wave function, 1s wave functions are positive in every direction. So guess what? If I'm taking the sum of these two wave functions multiplied together, ta-da, it's symmetric in every direction, and it's positive in every direction. So we have symmetric around the center and then positive everywhere. So this is actually a fairly nice system, as long as you remember the fact that should be a 2. So we can also look at this in the asymmetric fashion. Well, because I'm taking the difference, what ends up happening is I have a positive wave function on one side and a negative wave function on the other. Now, the most important take-home part of this is that what it generates is in the middle a node where my wave function is equal to 0, which means my probability at this point is also 0, which means that in order to make room for the fact the electron can't be along this plane, I'm going to be spending more of my time with the electron out here on the nodes. And again, this means that I've got less electron screening in between these two positive charges. So these two nuclei are going to be much more attracted to go out towards the electron density and are going to experience a great deal of repulsion between these two net charges. As a result, the asymmetric function is rather unfavorable. In comparison, the symmetric wave function is going to have an increased probability density in the middle. And as a result, it's going to be a little bit lower in energy, as these two nuclei are going to be attracted towards this density, which will bring these two nuclei as a whole closer to each other. So, because this symmetric combination experiences the energetic lowering, we are going to try and focus on the symmetric form for now, and we'll deal with this asymmetric form a little bit later. So let's kind of try and diagnose this wave function. And for now, we're going to ignore the normalization constant. So again, I'm going to have a symmetric combination where, again, this overlap is going to form a stable molecule. Now, let's try and diagnose what this looks like a little bit more mathematically. So, turns out that each of these atoms are hydrogen. I know what the hydrogen 1s orbital looks like. Turns out it actually isn't that bad. So for the first electron being around atom A, I'm going to have the 1s orbital. Again, we're going to focus on we have a radial part, which is going to be the main focus, because it turns out the angular part is just the normalization constant. And then this RA1 is going to represent the distance of the first electron away from atom A. And B2 represents the distance of the second electron away from atom B. And similarly over here, the distance of the second electron from atom A and the distance of the first electron from atom B. And again, we can turn this into a ratio by dividing by the Bohr radius. So when we put this together, it's a rather straightforward equation, but let's be honest, it's also a little bit messy. So one of the first ways I can simplify this out is by taking all of these normalization constants, which are shared by everybody. So I can multiply these two together. That gets rid of the square root, and then I can pull it out front. And when I do that, well, I get this nice constant out front, which I'm not going to worry about too much because it turns out this is still the unnormalized wave function. And then what that leaves behind is these two exponential terms on either side of the additive portion. So again, these are going to be the distances of each electron from each atom center. Now, it would be rather nice if I could go ahead and combine these two functions. So we can use our exponential rules and collapse this guy down a little bit more. And when I do this, what I have is the exponential of the distance of electron 1 away from atom A plus the distance of electron 2 away from atom B. So this guy is going to be, this function is going to have the greatest probability when electron 1 is right on atom A and electron 2 is right on atom B. But the problem here is I also have this portion, which is going to be the greatest when electron 2 is around atom A and electron 1 is around atom B. So when you add these two together, it gets a little bit problematic because electron 2 wants to be both around atom A and atom B, and the same thing with 1. And that's what ends up producing a greater density in the middle as it drags each of the electrons near the other atomic center. And so we can view this by what each of these functions looks like individually. And then we can add everybody together, and we end up with a net new wave function with a highly enhanced probability density right here in the middle. And that's really what we're looking at when we're looking at the symmetric combination, is we're enhancing the amount of electrons in the middle, which then enhances the attractiveness of each of the nuclei towards that extra density, bringing them a lot closer together than they would normally be. And that's the major idea of a bond. But we run into a slight problem. We forgot about Pauli. Never forget about Pauli. So we have to remember that the Pauli principle is going to mandate that since electrons are fermions, they have to be antisymmetric to wave electron exchange, which means if I turn this 1 into a 2, and this 2 into a 1, and continue that throughout, I should get a negative sign out in front. Unfortunately, as you would expect from the symmetric combination of the orbitals, it is not antisymmetric to exchange. Means I forgot something. So we have to solve this problem the same way we did last time. We have to deal with the antisymmetric component, and we can do it by bringing in spin. Because turns out that we can bring in an antisymmetric spin component, which, as a refresher, is going to be the antisymmetric combination of alpha and beta spins, which, again, as a refresher, if you want to revisit the singlet triplet splitting lecture, or singlet triplet spin lecture, this particular combination means I form a paired spin. And while a certain energy penalty comes along with it, it does allow us to pair my orbitals and make the symmetric combination, which is a big win. So in order to pair my orbitals together symmetrically, it turns out that my electrons also have to make a paired set. So this is where we get this idea that electrons have to have this kind of paired exchange. So when we put this together, what this is going to do is help show that when we're talking about a hydrogen bond, composed of two 1s electrons, we're going to have to pair the spins to increase the overlap between the two wave functions, which when we put it together makes a net bond. And so this is our first molecular bond. Now this one got a special name because if you look at this bond viewed down the axis, so down the bond, or the z-axis, as we're going to increasingly develop, this looks like an s orbital. So early physicists gave this the name of an s orbital in Greek. I introduce the sigma bond. So we've now introduced the idea of sigma bonds. We now have a full, complete, and operational wave function, which we can take forward. So next time, we're going to take our valence bond theory to the second period and beyond. Let's make some molecules. All right, take care and stay healthy.